All right, guys. So today we're going to kind of really quickly go through this replicating to some degree, right? The Arboskin Pavilion in your lesson. And this is as you can kind of see, it's a triangular panel, but the way it's arranged is in a sort of hexagon configuration. Okay. You can kind of look at some of the other things that are in your lesson here, right? But we're going to kind of go through this particular definition really quickly. Okay, so I have a dummy surface here, sort of long, but it doesn't matter. We can always retransfer this, right? So under params geometry, I'll drop in a surface component as the input, right? So right click, set one surface, click that, right? And now it's sort of linked in, okay? And with most of you should have a lunchbox installed. So if I can find my lunchbox here, right? Under lunchbox, there are the panels. And the one that actually looks exactly like the one that we see on the Arboskin Pavilion is the tri-B, right? So hexagon configuration. As you can see, there are other ways, right, to organize the triangles, okay? So very simply, this goes in the surface input, right? And if you kind of want to see things a little better, you can always take your input geometry and hide it on the Rhino side and hide the input container as well. So turn off the preview, okay? So that's that. Now, this depending on the proportion of the surface that you put in. If it's completely square, it might be stretched slightly differently. So you can kind of change these U and V subdivisions using a slider. So I usually just double click 0 smaller than 10, for example. Copy paste, Control C, Control V. And this usually like that is sort of 10 by default, right? So you can kind of adjust it if you want it to be taller or shorter, wider. Like that might look a little bit more equilateral, right? Now, this isn't a perfect sort of geometry kind of solution, but it'll get you into the ballpark as far as proportions are concerned. Okay. Now, this has a basic output. You can see are untrimmed surfaces, right? So if I bake these in, we can kind of take a panel look at it. If I bake these I would just get kind of separate triangular pieces, right? Big ones on the side, in the middle, and then these sort of half triangles on the edge, okay? So one of the components we use a lot for this, working with, in particular, the lunchbox sort of panels is the deconstruct brep component here. So dbrep, right? And what this does is that, and I kind of have this habit of hiding things as I go, Control Q, is that it breaks things out as either faces, right? So the actual surfaces, triangular surfaces, edges, right? So each triangle has 3 edges, and vertices. Each triangle has 3 vertices. Now again, using a panel, you can see this face, the way the data is organized, right? Each untrimmed surface, each triangle is in its own list, right? The edges, as you might imagine, all 3 that are associated with the first one are in the same list. Vertices, all 3 that are associated with the first one. This one is 0 to 0, so it's actually probably that guy, right? So it's, this sort of first triangle is probably that one. But these are the 3 vertices that are associated with it. Okay. Now, this just gives us the ability to select granularly the things we want to work with. Okay. Now, in the case of the Arboskin Pavilion, what we're going to do is we're going to take these triangles, we're going to find its area centroid, and then we're going to offset the area centroid using the surface normal direction, right? Now, the reason we want to use a surface normal direction is, well, if everything is flat, to do this, you just need to give it a z vector. But let's say if we're trying to apply this pattern to like a cylinder or some kind of organic surface, then the surface normal directions would all be changing, right? The surface normal direction is not one consistent vector, but it depends on where that point is, okay? So the reason we're using this is just so that this definition is a bit more robust and can be applied to many more situations after the fact, okay? So as common, we'll use a area component, right? We'll look at the area centroids of each individual face, right? So this gives us all the area centroids of each one of these individually, okay? And then we will use the evaluate surface, eval surface component here. And the surfaces we're evaluating are basically each triangle, right? So that's where this goes into here, okay? And the centroids will give us the UV coordinates that you're going to evaluate based off of, right? Now, when you first do this, it's going to look like this, right? It's going to kind of go all over the place. That's because we didn't reparameterize this input surface. If we reparameterize, right-click on the S and click on the reparameterize, then everything actually should work correctly, right? Just so that the kind of surface coordinate systems are, let's say, recalibrated, right? Now, so these guys will give us at that point, right, the point, right, at the UV coordinates that it's giving us, or the area centroids over here, the normal direction, and also UV coordinates, UV directions, this sort of stuff, okay? Now, out of here, what we really need is the normal direction, right? Because it will tell us, okay, which direction is shooting basically perpendicular to the surface at that point. So we are going to take the area centroids and move them. So move, right? So geometry and a translation vector, right? So the geometry we're trying to move are the area centroids. So you'll see like by default, it already kind of moves upwards, but we want to be able to control the amplitude of this, right? So of course, we'll use a multiple, we'll use a multiplication, simple multiplication, right? Into the translation vector. And we'll take the normal vector from the eval surface over here and add a slider, 0 smaller than, let's say, 20.0. Oh, it doesn't have to be that big. This depends on your scene scale. Okay, so it's going that way, right? It's going in the opposite direction. That direction, you can either just reverse this into a negative or go back into Rhino, show the surface you were working with, and just like flip it 180, and it will do that. Okay, now this should be the right direction, up, down, right? So we can now kind of control, let's say the pyramids, right? The pyramid heights. Now, finally, right, just in terms of geometry, the final step here is actually just to use a extrude point component. And what we're going to do is we're going to take the edges, right, the outlines of the triangles and extrude them to a single point, which is this floating point in the air, right? So the point obviously is coming from here. And then we're going all the way back to here, the edges, right? The edges of the B rep. And this goes into there. And now, let me hide all this stuff. Q. What you'll see is we should have pyramids, right, that are populated across that surface. Of course, you can still control how tall these pyramids are, okay? And that's the basic geometry, right? This is the extruded sort of pyramid, okay? Now, of course, in the actual kind of Arboskin example, it has sort of openings, right? And so we can kind of go a little bit further and look at, well, how do we use these? How do we generate that, right? So while the basic kind of, right, definition is sort of fairly straightforward up to here, right? So you can kind of like say, okay, well, that's kind of a group, right? That's the base definition. This other stuff is just kind of extra, okay? So what we're going to do here is, and again, I'm going to kind of sketch on top of here. So each, let's say, pyramid, right, is going to have three sides. So that's the top corner, right? And so there's kind of three edges, right? And we're just going to find a way to kind of evaluate a certain random point on these three edges, right? And reconnect them and to get a smaller triangle that we can use as a trimming surface, right? To basically lop off the tops of a pyramid, okay? So that gives you the kind of like conceptual direction. All right. So as you can imagine, we can actually just draw these lines. So line, 2-point line, right? The normal sort of 2-point line, right? And we know that one side of the line is these tips, right, of the pyramid, and we're going to draw from the base or one of these vertices to the tip of the pyramid, right? So that means that the sort of direction of the line kind of does matter, right? Where we're kind of drawing this from. So we know that we want to end at the tip of the pyramid, right? So the sort of moved or these sort of vertices, moved centroids should be going into B, right? And then again, going back to the deconstruct Europe component, because this gives us all the different vertices, right? So what we're going to do is we're going to, and you'll see what this does, is if we do this, right, it will draw those lines, right? But and this will do them kind of most of them or all of them sort of automatically, right? These lines that are going from the vertices to the sort of offset centroid, right? But what we kind of want to do is actually be able to kind of control these individually, right? So I want to be able to select, well, which one is it? So list item, list item over here, coming from the vertice, this goes into here, that goes to there. Okay, so what this should show is that's sort of edge 0, edge 1, and edge 2. Okay. Now again, if you kind of want to see the in relationship, so this is one of the triangle vertices, right? 1 and 0, right? So this allows us to control which of the edges we're actually working with, okay? Now, this eventually we'll just do one of these, and eventually what we can do is actually copy paste the same thing for the rest, right, of the kind of definition or the other two sides, okay? So now you may recall that in the past we've used under curve analysis, point down curve, right? This thing to be able to grab, right, a specific point on the line, right? 0.5 is the midpoint, right? And of course, in this case, right, going from 0 is where you start your line, 1 is where you end the line. So you're able to kind of address things this way, right? However, there's a sort of different way to do this. So that was the sort of point down curve, the evaluate curve version, right? This basically kind of does the same thing, exact same thing, except, right, instead of being a slider, right, you're kind of giving it values, right? And the reason we're using this is because we're not trying to manually control this, but actually do perhaps some randomization, right? Okay, so random. So this is the random component. The icon's funny because it's a cat in a box, right? It asks for a domain. So basically like what is the range of numbers that you're trying to kind of control it against, the number, how many random values do you need or want, and the seed is sort of a random number generator kind of thing where you can kind of change it to get different results, right? Okay, so I will put this here so we just can kind of see what kind of output we're getting, right? Right now, there's nothing. This is a bunch of different random sort of line segments, right? And here we can evaluate these curves. It's missing the parameter that we want to give it. You can give it the random number, right? Now, just to note kind of what this is doing at the moment, and you'll see a point pop up right over here, is that it's using this random number 0.771094 to find that point on the curve, right? To eval that point on the curve. But there's only one random number, so all the curves have the same quote unquote random point, right? And this has to do with how the data structure works. This has to do with how we're only giving it one number. So it's applying that one number to everything, right? Now, so what we want to do is generate enough numbers here to basically cover all the lines, right, in this sort of group. So we have to know how many lines are in here. Now, I can hover over this and say, oh, that says 99, right? Locally defined values, right? So I know that there are 99 lines, right? So what we can do is there is a list length component. So this one, right? That will give us the length of a list. And so basically tell us how many of these are there. Now, at first it won't work because it gives you, oh, there's one in that list, one in this list, one in this list. So what we have to do is actually flatten this, right? So if we flatten it, they'll give us 99. It'll say, hey, there are 99 things now in this sort of flattened list, right? Which is kind of what we want. So here, this goes to there, right? And not only that, but also we need to flatten this list as well because now, right, this is a flattened list of 99 numbers. Now the random number generator is creating 99 random numbers, right? Now, right now, it's basically doing 99 random numbers on every single line here, as you can see, right? So what we're trying to do is to get the data to match. So we have to do the same thing here, flatten this list. So in this input, flatten it. And now it will basically go one to one. So the first one will be 0.7, the second one 0.4, the third one 0.1. And as you can kind of see, right, the points that are on these lines, the locations are now all kind of randomized and different, right? Which is great. Okay. So thus far, most of this, and you can add a slider here, 0 smaller than, let's say, 20 for the seed of the random number generator. This just kind of changes different random configurations, right? This doesn't really, just like if you wanted a different randomized scenario, this is how you would do it. Okay, now, okay. Now I'll go back to this, the domain of random numeric range, 0 to 1, right? So it's generating numbers that are ranging from 0 to 1. So if we kind of look at, well, actually look at here, 0.2, right? So 0.1, 0.5, 0.8, right? So what if like I don't want some of these like points to be so far down, right? Because if they get really far down, then we're cutting into these pyramids a lot, right? So I just want to be able to kind of control, let's say the range, right, of where these pyramids actually cut, right? So that's where this input actually comes in. And this is super simple and straightforward. Double click, right, double slash, right, to, again, it's a panel. And I'm going to do 0.6 to, let's say, 0.9, right? And this is basically just a text string that says, hey, instead of random numbers that range from 0 to 1, let's just have random numbers that work between 0.6 to 0.9. And voila, you see right away this changes. So the smaller numbers are 0.6, the bigger numbers are closer to 0.9. This kind of controls the, let's say, the cutoff point, right, where all these points are. So it will never ever go below 0.6, and it will never go beyond 0.9 on the other end, right? Even if we randomize it, you'll see we're able to kind of control the, let's say, the range of where these points end up being. Okay, great. All right, now this can be reused, so I'm going to kind of stick it here. But basically this whole assembly gets duplicated twice, 3 times, right? Except we're going to go from 0 to 1 and 2, and now we have the entire thing, right? This range thing, right, still controls across all 3 of them, right? So if you change this, you say, oh, I want my cuts or openings to be a bit bigger, then you can change this to, let's say, 0.4. Say okay, and then some of them will go a bit deeper, right, into the pyramid, okay? And you can still change the seed, so like not all of them are the same, so I would change this. So the not random numbers that you get between the 3 sides are actually different, and you get a bit more range and variety, right? And then finally, we will actually just construct a surface from 4 points. So 4-point surface right here, surface freeform, right? And we just need to give it these 3 points, right? So 1, 2, and 3. And so this actually will represent the trimming plane. So you'll see some are big, some are small, right? That kind of just represents the sort of height. And so you can bake this, right? You can bake the actual, just the original tri-B sort of panels, right? Sorry, not the tri-B panels, but the extrusions, these extrusions, right? And you can use these surfaces to trim off the extrusions, right? And in the end, what you'll get is basically something that's very similar. We can kind of sort of use this, oops, we can use this as a way to just like visualize. Oops, sorry, I did so. Just to visualize, okay, well, how big are these openings? And as you can see, as I change the speed on these, right, one of the edges cycles around, the other edge, right, edge 1 and then edge 2. So you can kind of change the randomness. Now, this is random, but of course you can actually do gradients, you can do attractors, right? The sort of logics are about the same. You're just kind of influencing the point, right, at which these are evaluated upon the edge line, right? Okay.